So this unit is about functions, and that makes it kind of a segue to calculus. Calculus is all about functions. We're really going to start that in the next unit. This one is more a set of kind of basics, uh, some stuff that will be reviewed for almost everybody, some things that might be new to some of you. So when we say something like y equals f of x, y is a function of x, that's how we would read that. What we're saying is that y is determined by x. We're saying, you tell me x, I'll tell you the y that goes with it. So like just an example, we might think that area of a square is a function of side length, right? That the area y would be equal to the side length x squared. That's an example of a function. That's kind of the words version. A slightly more precise definition would be f of x. Let's say f of x equals y. So that's a relationship between x and y. And two things need to be true for that relationship to count as a function. It's a function if it takes each, let's underline that important word, x, it's an element of some domain set x. So each small x is an element of set big X. We're going to call that the domain. And maps it to exactly one. That's our other really important phrase here. Y value that's part of some set, big Y, that we're going to call the range. Okay, so let's just admire those two underlined phrases right now. What are those? What are they ruling out? Okay, so one thing that a function has to do is it has to assign a y value for every x. Okay, so again, if you think about a function as a conversation, we're saying that the function has some domain, some set that it applies to, and most of the time for us, it's going to be the set of real numbers. Okay, so you give me some number x, and the function has to tell you a y that goes with it. The function can't say, "Ooh, I don't know." The function has to give you a number. Okay, if not, either you don't have a function, or maybe you need to like work with your domain to make it a function. The other thing that we need is that the function can't say, oh, well, maybe it's 3, maybe it's 4. The function has to give you one clear answer. So the function takes each x, it always assigns it a y value, and it always assigns it only one y value. Okay, great. Seems pretty straightforward, but the cool thing that this gives us is if f of x is y is a function, okay, so if it has those two properties, that it tells us a y value for every x and it tells us only one y value, then if we start with a equals b and we apply the function to both sides, it will still be true. Okay, so if something's a function, you can apply it to both sides of an equation. So you could kind of add functions to the toolkit of algebraic operations that we learned in Unit 1 here. So if we start off saying that a and b are the same thing, and we know that f is a function, then we know that f of a is going to be the same as f of b. Very cool. But don't get too excited here, because it doesn't necessarily work in reverse. You can't necessarily go the other way. just because if you start with f of a equal to f of b, that does not necessarily mean that a equals b. And that example of an area of a square is an example that shows how this reverse implication doesn't work. Let me, in fact, comment on this sort of open arrow. We'd read that implies. Let's pick a nice color for that. Okay, so this open arrow means that A equals B implies that f of A equals f of B. And when I'm writing it with the arrow sign through it here, this means it does not apply. Okay. And where you can see that is with f of x, particular function we're thinking about being x squared. Well, it is true that if you start with a equals b, that implies that a squared equals b squared. That's great. Okay, switch to our danger color here. But you can't go the other way. If a squared equals b squared, that doesn't necessarily mean that a equals b. And well, you can sort of think of examples. You could have a squared and b squared both being 4, but a could be 2 and b could be negative 2. And so what we would say here is that f of x equal x squared, it is a function. Okay. We can square any number, you give it an x, we'll multiply by itself and tell you what it is, and it's only going to be one thing. It's not going to be this or that. So f of x is a function, but f of x equals x squared, but is not invertible. So last point I want to make about functions that may or may not be invertible. Let's just sort of summarize what I'm getting to intuitively here, that you can have a mapping from x to y. It satisfies the things we need it to satisfy to be a function. You might want to ask, well, can it go the other way? And the answer is sometimes. It can go the other way if when you switch the roles of x and y, the criteria for a function, those two criteria, always give an answer and always give only one answer, are still met. So let's write that systematically here. Okay, so let's do the definition of what it means to be invertible here. A function f of x is invertible if, again, two things. One, each y in the range of the original function. So each y, little letter indicating that's a number. This thing that looks like a euro sign actually means it's an element of a set. And the big letter y here indicating that's the set that the little y's are members of here. Each y in the range is associated with some x in the domain. Okay, so it's a function if the inverse mapping gives you an answer in the domain of the original function for the y in the range. And two, it gives you only one answer. So let me write that up kind of a nice compact way. If x equal x prime, then f of x equals f of x prime. Another way to say this in words would be no distinct x's give the same y value. Okay. So thinking about things that are functions but aren't invertible. So something that is a function but isn't invertible because it fails this first criteria here would be something like y equals 5. Fails this criteria. Okay. Y equals 5, it's not a super exciting function, but it does actually fit the criteria. No matter what x we give it, we can say x equals 1, y equals 5, x equals 3 million, y equals 5, x equals negative 8,000, y still equals 5. It is giving an answer for every x, and it is only giving one answer. It is in fact giving the same answer over and over again. So y equals 5 is a function, but it's not invertible because all of the other real numbers in the domain are not used. Okay, there's no x that gives us 4 or 3.29 or anything like that. And the second criteria for a function to be invertible, well, we just saw an example of how it fails with y equals x squared. Okay, this fails because we can have 2 equals negative 2. Okay, so you can have 2 distinct x values, but they do indeed give the same y value of 4. So that's really all I want to say in this kind of like introductory overview about functions. Maybe the last thing I want to do is draw attention to language that I'm starting to use, and you're probably picking up from context. When we're thinking about functions, we're thinking about a relationship between two variables, and they do play different roles. Okay, so we've got the domain variable, which is the x, and sometimes we call that the argument of our function. So let's one last page here. Y equals f of x. X is, let me say, the argument of the function. Y we might call the functional value. X is from the domain. Y is from the range. Getting a little bit farther afield and using language, maybe more from statistics than actually from math, we might think of x as an independent variable, something that's kind of coming from outside what we're trying to understand, and y as a dependent variable. And of course, x and y are like conventional letters that, and there's no reason to do it otherwise. We use x to represent the domain and y to represent the range, but we can use any letters we want. Okay, it's the logic that matters. The final thing I'll say, I think that's like the third or fourth time I've said it's the final thing, but I think this is really the final thing. You're going to see in the videos going forward that I'm often going to be using graphs to illustrate functions. And so let me maybe just put a quick little graph here. The convention there is that the argument goes on the horizontal axis, so much so that we often will just call this the x-axis. We think it is, and the functional value goes on the vertical axis here. We will be using graphs to look at functions, and I would actually recommend this to you when you're working problems, to go back and forth between looking at functions in terms of their equations and in terms of their pictures. You'll see in some of the videos just to come, sometimes I'll have pictures prepared in advance for you because you may have noticed I'm not the world's greatest artist. Other times I'll try to draw them. I actually find if I'm trying to understand something, drawing it out myself by longhand helps me. Sometimes when it's really difficult though, and I'm not sure how to do it, I might use a program to help me. So there's a couple of links on the website, or one link on the website to website Desmos that will help you with graphing. If you have a Mac, there's also built-in, it's called Grapher, uh, built-in app that will help you do graphs. So if you can get in the habit of drawing pictures to go with the functions that you're working with, that'll help things become a little bit more